Hi. So in this set of videos, or in this particular video, we're going to be looking at some preliminaries for some of the things that we'll be looking into for the following set of videos that I'm going to do. So in particular, we'll be looking at so what is a second order elliptic PDE in divergence form, and why do we need to, or why is it important to study these things? And we're gonna do a brief introduction as to what weak solutions are, what weak derivatives are, what Sobolev spaces are. So all the sort of standard stuff that we need to discuss more of the theory in the upcoming videos. And we're also gonna do a brief recall on like different notions of continuity. Okay, so let's get started. So for this one, for this set, we are gonna be looking at equations of the following form. So let's write that down. It's gonna be minus divergence of a grad u. Okay, so u here is a scalar function, so grad u is a vector. A here is some matrix, and in our study, it's gonna have like certain properties, but we're gonna discuss them as we go. Plus cu is equal to f in some set omega. So here omega is gonna be a bounded open connected set in Rn. And we impose some boundary conditions. U is equal to 0 on the boundary. So we're going to look at this problem. So this is an example of what we call a second order elliptic PDE in divergence form. So we say that it is in divergence form because the second derivatives occur in this term here. It's going to be like divergence of something. So yeah, basically that's it. There is like what we call elliptic PDEs in non-divergence form, and the theory for that is actually very different from for those in this particular form. So this is a simple one. It's linear. So A here doesn't depend on U, and we don't have any like other first order terms. Okay. So let's call this equation star. Okay, so we want to ask like why these equations? There are countless different PDEs to look into, and to answer that, in the study of PDEs, the choice of which PDE to study is really dependent on how significant are the applications coming from it. So yes, it is true that there are like countless PDEs to look into, but the reason that we're looking into this PDEs of this particular form is that they model a lot of things. So they model things from physics or chemistry or like engineering or even economics. So, and we're gonna list here some of the motivations for studying this this family PDEs. So let's write that down. So we want to ask like why these PDEs. So firstly, I'm gonna say that this PDE appears a lot in transport phenomena. So this looks into the transfer of some quantity in some medium. So this comes up in physics, chemistry, or like chemical engineering, stuff like that. And you sort of want to look into like how energy is being transferred in some material, something like that, which could influence a material's temperature. Or you could look into, for example, like some kind of a reactor, and you're looking at mass transfer, like how it's like some species A is like being diffused or affected or consumed or produced or something in a reactor. So let's write that down here. The connection to the PDE that we're looking into is when you do mass and energy balances on a differential element, you get these PDEs. So you get equations like star. So what do I mean when I say like do a mass or energy balance? So usually what engineers, for example, would do is a differential element would be some kind of a little thing. So it depends on the geometry of the system, what is like most convenient to look into. But usually it's gonna be some kind of a cube or something. So what you sort of do is it's like an accounting thing. So you account for things going inside, you account for things going outside, and you look at some kind of a balance equation, like the rate of accumulation of some quantity, let's say f, in time is gonna be equal to the rate going in minus the rate going out, plus some accumulation terms. Now, if you do this for a differential element, and there are like other things, you typically get PDEs of the form star, or like star with other terms. In particular, let's see. The terms appearing in equation star actually have physical meaning. So, for example, the term divergence A grad U here is interpreted as, sorry, wrong color. This is interpreted as a diffusion term. So this is can be thought of the transport of material through like molecular processes. So this is molecular transport. And in the particular case of like, let's say, we're looking at heat, we're looking at the transfer of heat in some metal. So the diffusion term would be conduction. So this is the transfer of energy brought by like the movement of molecules, but not like the bulk movement of molecules. So the diffusion term, it's gonna be like represented by the second order term, this divergence of something term. Now the other terms, they are present in equation star. So we have something like Cu. So in practice, this is often interpreted as a reaction term. And say an example for if you're looking at mass transfer, let's say like in a reactor, this term accounts for like consumption of a certain species or like production of a certain species because of some kind of reaction. Now, the other term appearing in our equation is F, and this is going to be the a source term, a source or a sink term. And going back to our like heat transfer example, it can be that there's like a heating element or a cooling element inside the medium that either produces more heat or consumes more heat. So yeah, what I want to say is that in the context of transport phenomena, when you do balances like in differential elements in order to sort of model the transport of mass or energy of some other quantity, you get these equations similar to equation star. And the terms arising in equation star have actually physical meaning. And of course, where it's not always going to be this case, so we're not going to look into, at least for this first set of videos, we're not going to look into equations with first order terms, meaning to say with first derivatives of u. And those terms, they sort of look something like, let's use a different color, let's use green. It's going to be something like some vector b dot grad u. So these are our advection terms. So these sort of describe the transport of something represented by u by some vector b. So we usually see this, for example, if some fluid flow is involved. So the bulk motion of fluid contributes to the transport of either mass or like energy in the system. So aside from transport phenomena, another like motivation that I kind of want to tell you is let's look at variational problems. So a lot of the problems in physics involve like minimizing some kind of an integral functional. So, um, so for example, in mechanics, I'm not a physicist, so I'm not quite sure, but for example, in mechanics, you have you minimize what you call like a Lagrangian, and minimizing this is going to be equivalent to like solving some kind of equations, which are the same equations that you get like when you applied Newton's second law, when you applied some kind of a balance of forces and stuff. So what I want to say is that lots of problems in physics these they can be modeled by minimization problems, or they can be written as minimization problems. So in particular, they're going to look something like this. Let's see if I have space here. Let's move to the next page. So it's gonna look something like this. You're finding something. You're finding u such that I of u, which is some energy functional of some sort, would correspond to the minimum value of I over all possible w, and it's going to look something like this. I of w is going to be something like integral over some domain omega L of grad w x dx. Here L is a function of a vector p, scalar z, and like a point in space x. Okay. Now one can show that solving this minimization problem is going to be equivalent to solving some equation. So, and perhaps we're going to look into that at some point if we ever like go to looking at Hilbert's 19th problem. But yeah, so we're not going to show here, but these minimization problems can be written as or is equivalent to solving some kind of a PDE. So in particular for something like this, one can show that it's equivalent to solving equations of the form sum I from 1 to n. So we are in Rm of the derivative of LPI. So this is the derivative of L with respect to PI. Grad U Ux, derivative of this quantity with respect to I. So this is a divergence of some sort. So this is divergence plus Lz, so derivative in Z, of grad U Ux is equal to 0. And these are what we call the Euler-Lagrange equations. And they actually look similar to equation star. In particular, it's going to be, it's also a second order elliptic PDE, but this time it's nonlinear. So this is something, this is quasi-linear, this is a quasi-linear elliptic PDE. And so yeah, so the reason that I'm like saying these things is to motivate like why is like equation star important. And the reason is like just from the examples that I gave, you see that like in transport phenomena and also here in like variational problems arising from physics, which involve some kind of a minimization and is in fact equivalent to like solving some kind of an elliptic PDE. So aside from it being quasi-linear, I also want to emphasize that it's something in divergence form. So this, like what I said earlier, this term here is a divergence of something. And this ties into Hilbert's 19th problem. So let's use what color? Let's use this. So Hilbert's 19th problem looks into the regularity of the minimizers of functionals, it's sort of abbreviated like that, of functionals appearing in the calculus of variations. And the reason that Hilbert asked this was I think during his time, people know that solutions to certain PDEs, like Laplace's equation, um, are analytic. So aside from them being smooth, they admit like a power series. So it's stronger than being just infinitely differentiable. So they're very nice. They're analytic, and other PDEs as well. If I'm not sure, if I'm not mistaken, maybe even the minimal surface equation that maybe they know back then that solutions are analytic, and like what I mentioned before, solutions to these PDE, so they're going to look something like this. They're going to be equivalent to minimization problems. So that sort of led Hilbert to ask, like, if I look at minimizers of functionals of this form with certain conditions imposed on L and such, am I guaranteed that the minimizers are analytic? And the solution to that came like many decades later. So the solution to this, so a lot of people contributed to the problem, but the final crucial one uh, was solved by De Giorgi and Nash, I think in the 50s, late 50s maybe, or and Moser did like a different thing, but is very sort of similar to De Giorgi's iteration methods in a lot of ways. So yeah, so let's write it down. So the solution came because of like De Giorgi, Nash, and Moser, and they all worked on this independently. So I think this is in the 50s or 60s. So decades after like Hilbert posed the problem. So the goal of this set of lectures is we're going to be looking into regularity of certain elliptic PDEs in divergence form. And we are going to look into two things basically. We're going to look at how do you get like regularity using perturbation methods, and how do you get regularity using the techniques that De Giorgi and Moser like came up with. And hopefully the discussion would lead into, okay, now with these results, like how do we solve Hilbert's 19th problem? Okay, so let's look at now weak solutions, because that is really what we're going to be looking into. Like it's sort of fairly easy to show that weak solutions exist, and then we put in the work to actually show that these solutions are better. But to start, like, what are weak solutions? Okay, so let's see. So suppose U is a solution of star. So when I say it's a solution, I mean like a classical solution. So the derivatives exist in the classical sense. Okay. Now we let phi be a smooth function, C infinity, infinitely differentiable with compact support in omega. Okay, so since this is a preliminary video, okay, so let's sort of explain what that means. So omega, we're starting with the assumption that, so let's draw omega here. So omega is some bounded connected open subset of Rn. So this is omega. What does it mean when we say that the function has like compact support? So there is a set, let's use red. There is a set K that is compact such that, so K is compact. So in Rn, compact sets are closed and bounded. So there's a set K such that K is compact, K is compactly contained in omega. So we're sure that it's of some positive distance away from the boundary of omega, and that the support of phi, which are the set of points x for which phi of x is not 0, this is contained in K. So the points for which phi is not 0, doesn't vanish, it's all in K. So outside K, you're guaranteed that it's 0. Okay? So that is what we mean when we say that we set phi to be something in C infinity 0. It's infinitely differentiable, and the set of points for which it is not 0 is contained in some compact set contained in omega. Okay. So we let phi be that function. So what we're going to do is we're going to multiply equation star by phi, and then we're going to do an integration by parts. So what are we trying to do here? We're trying to find some equation that U solves. So we start with the assumption that U is a solution to star. We're just sort of asking, okay, what other equation would U possibly solve? Okay, do I have space here? Okay, yes. So multiplying star by phi, and then we integrate, and integrating over omega, it gives us, so you'll get something like integral over omega of negative divergence of a grad u. So you multiply this by phi plus cu times phi is equal to integral over omega of f phi. Okay, now what do we do? So the solutions, So we are trying to develop the notion of a weak solution, and as the name implies, it's a weaker form of a solution, meaning to say that hopefully we're going to require less from you. So we're going to use this little trick where we look at the second order term. So the second order term is integral over omega of, let's disregard the negative sign for now, divergence of a grad u times phi. So we're going to do an integration by parts. And what that does is to sort of pass on one derivative from u. So we're going to pass on one derivative from u because at this point, u has like two derivatives. So we're going to pass one derivative of u to phi. So let's see, how do you do that? So just from calculus, assuming that everything is nice and smooth, the calculations that I'm going to do here are valid. So something from calculus, a divergence of a vector times a scalar is equal to divergence of the scalar times the vector minus the vector dot with the gradient of the scalar function. And then we're going to apply the Gauss divergence theorem for this one. Apply Gauss divergence there. So it becomes a surface integral, and then we have phi a grad u dotted with n, and this is the exterior normal. So this is just a normal vector pointing outward. So let's just draw a picture here, quick picture. So if this is omega, inside this omega, this is the boundary, n would be something like this. This is n, pointing outward. Okay, so this is just by Gauss divergence. And then we have minus this one. Now, remember, what is phi here? So phi is a function with support contained in some compact set in omega, meaning to say that it's 0 on the boundary. So in fact, this term is 0. So we have that this integral is equal to this one. So plugging that back into our equation, and note that we start off with negative divergence. What we eventually get is something like this. So we have integral over omega of a grad u dot grad phi plus cu phi is equal to integral over omega of f phi. So what do we have here? We have is that if u satisfies star, then it also satisfies this equation. Okay. And the crucial trick that we did was this integration by parts thing, where we passed on one derivative of u to phi. Look at phi here. We have grad phi now. Okay, so just some points. Note that we can only do this. So that's a remark. We can only do this if the second order term is of the form divergence of a grad u. Or in components, this is what? This is sum over ij of derivative in I of aij derivative in j of u. Okay, so and the reason that I'm pointing this out is that this is very crucial because the fact that the second order term is of this form allowed us to use the formula of writing this in terms of this and that. That is the step that passes on the derivative to the test function. Okay? Okay. Now, not all PDEs can be written in that form. So, in particular, let's look at the second order term written in components. So we have something like sum over ij of derivative in I of aij derivative in j of u. So if I do the differentiation here, what would that be equal to? So this is sum over ij of derivative in I. Suppose that aij is differentiable. So I can do this. And I have partial ju plus aij partial ij u. So I have here a first order term. So this is a first order term because it only involves like first derivatives of u, and this is now my second order term. So this can be written as some lower order term plus so this is actually the trace of in most instances a is going to be symmetric, so I'm not going to write like the transpose and stuff like that. So this is going to be the trace of a times the Hessian of u. Let's write it as something like this. So it's still an elliptic PDE, but this is actually what we call something an elliptic PDE in non-divergence form. Now, this is very important because if you have a PDE in non-divergence form, in theory, you can write it in divergence form, provided that aij's are differentiable. So you can just do like some calculus in order to write it in divergence form. However, that is not always the case, and in most instances, you only have like weak conditions on aij's. So you cannot write this back into divergence form. So, and so the trick that we had before, where you're using this integration by parts trick in order to pass on a derivative to the test function. So this doesn't have a derivative, you end up with grad phi. You cannot do that in this case. So my point here is, so weak solutions are in a sense a weaker form, a weaker notion of a solution, but it doesn't apply to all PDEs. It doesn't even apply to all elliptic PDEs. So there is a family of second order elliptic PDEs for which you don't have like a notion of a weak solution. So it's only applied to things in divergence form. And the study of elliptic PDEs in non-divergence form is very different, and we might do that in a future video. We're going to look at maybe like strong solutions or like viscosity solutions in order to like tackle these. Okay, so that was a segue. Let's go back. Okay, let's see. So let's write down what we have now. So what we have is, let's use this color again. What we have is, so if you is a solution of star, then we have that you satisfy the following. Integral over omega of a grad u dot grad phi plus c u phi is equal to integral over omega of f phi. Okay, so for every phi that is infinitely differentiable with compact support in omega. Okay, so let's note some observations here. Okay, so let's use purple. Okay, so the first observation is for the equation. Let's look at the equation itself. So u only has first order derivatives appearing. So remember, I started talking about like, so we're trying to figure out what other equation u solves, provided that it solves the original equation. And here we have some kind of an equation, kind of a weird one because it's an equation where we're saying that this is true for every phi, and this phi is what we call a test function. Now looking at the equation here, u only has first order derivatives. So it's just this one, grad u. So coming from before where you have divergence of a grad u, here you just have like grad u. So u only has first derivatives appearing. And in fact, these derivatives, so let's put quotation marks there, they're not derivatives necessarily in the classical sense. So not necessarily in the classical sense. And what do I mean here? I hope I didn't make it quite confusing because I said that u is a solution to equation star. Okay, so let's like backtrack for a bit. So if u is a solution to star, I know that u would solve this. Now, okay. Now let's just look at this equation. What do I need for u to be in order for this equation to make sense? And this can make sense even if u doesn't have second order derivatives, because like as we've noted, u only needs to have first order derivatives. So you don't see any second order derivatives appearing here. And I want to say that these derivatives need not be derivatives in the classical sense, where derivatives are like what? They're limits, they're slopes of tangent lines and stuff like that, or they're like limits of secant lines and stuff like that. So they need not be like that in this case. And in fact, when we say this can still make sense even if u only has weak derivatives. So even if u only has weak derivatives. Okay, so what are weak derivatives? So this is going to be a very brief intro as to what weak derivatives are. And since we're looking at second order elliptic PDEs, we're only going to be looking at first order weak derivatives. Okay, so given some u in LP, okay, so from our real analysis, what does this mean? What does this mean? That the integral of absolute u to the p is finite. So given u in LP, its weak derivative is so the weak derivative of u partial I of u is a linear functional. So meaning to say it's gonna be a function from the set of infinitely differentiable functions with compact support in omega to R. So this is linear. And its action on some C infinity 0 function is defined as, so the action of this on some function phi is going to be equal to negative integral over omega of u partial I of phi. For phi in C infinity 0 of omega. Okay. Okay, so let's see, what does this mean? So we start with an LP function, and we're saying that its weak derivative is not gonna be some kind of a slope anymore. It's a linear function, so it's a function that takes in another function, something in C infinity 0, and gives out a real number. So it's a linear function, so it's linear, okay? And its action, so its action in this, so when you evaluate this at phi, for phi in C infinity 0, it's this one. And note that this is well defined if U is in LP, just by Hilbert's inequality. Okay. So what I want to say is, even if U is just in LP, you don't have any differentiability properties, that it still makes sense to talk about the weak derivative of U. So the question now here is, thus or when does have an LP representative? Okay. Because here it's sort of defined abstractly. It's a linear functional, which is very different from what we're used to. So what this question is asking is there some G in LP such that G applied, the integral of G phi is equal to negative U partial I phi for every phi in C infinity 0 of omega. Okay. Now, okay, so let's see. So when is this true? So clearly, okay, let's see. So clearly, if U has classical derivatives, let's say U is in C1, then the weak derivatives are the real derivatives. So the weak derivatives, they're the classical ones. They're the same. Now, what if U is not in C1? So now we introduce the notion of Sobolev spaces, and when we study PDEs in these set of videos, the solutions would come from this space of functions, this set. So if U is not in C1, we look at Sobolev spaces. So what are Sobolev spaces? So we're only going to look at first order weak derivatives here. So I am gonna write it as W1P omega. Here P is between 1 and can be infinity. So these are the functions U such that U is in LP and its derivative, first order derivative, so grad U, is in LP. So, and what that means is that all components of U are also in LP. And these are to be interpreted in the weak derivative sense. So we were asking before, like, when does a weak derivative like have an LP representation? So we're calling the set of functions for which that is true. The answer to that is okay. This function has an LP representative. We're collecting those and calling it like Sobolev spaces. So this is a very brief way of defining them. But in essence, this is what you need from them. So Sobolev functions are functions that are integrable and whose derivatives, weak derivatives, are also integrable. So again, these are weak derivatives, not classical derivatives. So they are to be interpreted in the distributional sense. Okay? Okay. Now we ask, like, why bother with Sobolev spaces? Like, why Sobolev spaces? So and the reason for that is we can do a lot of things with Sobolev spaces. So for example, you can have a notion called trace. And trace is a generalization of boundary values. So when you're looking at PDEs, you don't only like look at an equation, you also look at some boundary conditions. So the boundary of a set, so if you have some omega subset of Rn, some open set, the Lebesgue measure of the boundary is gonna be 0. And LP functions are defined almost everywhere. So it's not straightforward, or it doesn't make sense for every LP function to have boundary values. Okay, so not necessarily have boundary values. But when we look at Sobolev functions, we can have this notion of trace for which if we apply the same notion to, let's say, smooth functions, they reduce to the to boundary values. So on Sobolev functions, this the trace allows us to define meaningful boundary values. And in fact, for smooth functions, the trace corresponds exactly to the boundary values. So this is one reason, like, why Sobolev spaces, because the condition that the derivatives are also integrable actually helps you in defining this notion of boundary values, which you cannot do just for LP functions, even though LP functions have a weak derivative. Remember that the weak derivative is defined as some kind of a linear functional, which would make sense for LP functions. But the difference between that and Sobolev functions is that the weak derivatives have an LP representative. Okay. Another important thing is, and this is very important, you have the Sobolev embeddings. And what these are they fall into two categories. So you have the continuous and the compact embeddings. But what they mean is, so for the first set of embeddings, these are going to be some kind of an inequality of some sort. So for the first set of things, what you have is that if U belongs in some Sobolev space, then what this means for you is that you have better integrability for U, meaning U to the P integral of this is finite for larger P. Let's put that in quotes, because there's a limit to how large it is. So for larger P. So you have better integrability, or you can have better regularity. For instance, you might be able to show that U is actually continuous, or more than that, it's actually like in C alpha, it's Hilder continuous. So the continuous embeddings allows you to say something, say better things about U. In particular, if U is in some Sobolev space, either you get better integrability for U, or you get better regularity. Like, is it now continuous, or is not just continuous but actually Hilder continuous? These other set of embedding results for Sobolev spaces, they have something to do with compactness. So in particular, the idea is boundedness gives you the existence of a subsequence that is convergent. So to give this more context, let's see. Let's note like a particular example. Let's look at the case when P equals 2. So, different color. Suppose I have a sequence of functions un that is bounded in L2. And what that means is, if you look at the integral of un squared, the supremum of this over n is finite. Or put in a different way, there is some positive finite constant c, such that the integral of un squared is less than or equal to c for every n. So that is what we mean when we say bounded. Okay, so bounded in L2. So from functional analysis, by the I'm afraid that I'm gonna butcher the name, by the Banach Aloglu theorem. Okay, I'm just gonna write it down. I think it's that, or like a corollary of that or something. You have that a subsequence exists such that u and k converges weakly to some mu in L2. So you have weak convergence. So remember, in finite dimensional settings, compactness can be characterized. So something is compact in finite dimensional settings if and only if it's closed and bounded. So in the infinite dimensional case, it's not that simple anymore. So one can show that the closed unit ball in infinite infinite dimensional spaces is not compact anymore. So it's possible to find like an infinite sequence of points in this infinite dimensional ball that cannot be made, like you cannot extract subsequence that can be like closer and closer together. So weird things happen in infinite dimensions, but compactness wise, so we have these theorems where you sort of still get the things that you expect in the finite dimensional case. So here, what you give up is, or what you don't get is full convergence in L2, but you have weak convergence in L2. So what does this mean? So what this means is that, given some phi in L2, the following holds. The limit as k approaches infinity of the product of u and k times phi is equal to u phi. So note that strong convergence in L2. Do I still have space? No. Okay. So note that strong convergence in L2, meaning to say un minus u squared goes to 0 as n goes to infinity. This implies weak convergence. But in the infinite dimensional case, Weak convergence doesn't necessarily imply strong convergence. So in the finite dimensional case, they're equivalent, but in the infinite dimensional case, they are not the same. Okay. Okay. Now, we are digressing a bit. We're talking about like uh, it's a functional analysis result on compactness. But for Sobolev functions, you get something more. So I'd like to think of analysis that way. Like, it really does feel as some kind of an equivalent exchange sort of thing. Like, you really don't get things for free. You sort of need to pay something in order to get what you want. So, so going back to what I was saying, now if you have instead that UN is bounded in H1, so this is a Sobolev space. So this is just W1, 2 of omega. So using our notation from earlier, what this means is that the UNs are, there's the squares of UNs are integrable and the squares of their derivatives are also integrable. So them being bounded means that the sup in n of integral un squared plus integral grad un squared, this is finite. So this is something stronger than the previous one, just boundedness in LP. Now, if you have this, you not only have weak convergence in L2 and in fact in H1, by the Sobolev embedding, you actually have that there exists a subsequence U and K such that U and K converges to U strongly in L2. So you get this convergence here. Okay. So my point being here is it's practical to work with Sobolev spaces because you get a lot of things. And what are those things? Like, let's see, let's go back. We get a notion of trace for which you can assign boundary values. You also have these embeddings for which if something belongs in a Sobolev space, you get better things. You get better integrability or better regularity. And you have these compactness results where boundedness implies the existence of a convergent subsequence. Whereas if you have some, in this particular example, if you only have something like bounded in L2, you only have weak convergence, a subsequence that is weakly convergent in L2. But if you have boundedness in a Sobolev space, you actually get something more powerful. You get strong convergence in L2. Okay, so it really is a nice place to work with because you get a lot of things. Okay, so going back, so we digress sort of a lot. So let's see, what do we want to say here? Let's look back. So we had this, we were saying that, okay, let's just focus on this equation and let's make some kind of observations. Like, what does U need to satisfy in order for this equation to still make sense? So we were saying that in this equation, U only needs to have first order derivatives, and that these derivatives they don't necessarily need to be the classical derivatives. They can be like weak derivatives. And we've discussed like what weak derivatives are. So for LP functions, weak derivatives are linear functionals. So then we ask, when does it have like an LP representative? Meaning to say that there is some LP function G such that the action on phi, the action here, is an integral precisely. Okay? And then we were talking about Sobolev spaces. So it's exactly these functions that we need. And why do we want them? Because we can look at trace, which are boundary values. We get lots of nicer things like better integrability or better regularity. And we also have some better compactness results. Like boundedness gives you the existence of convergent subsequences. So it's very nice. Okay. So going back, let's see. So what is our original equation? Going back, we have something like A grad U dot grad phi plus cu phi is equal to f phi over omega. So let's make the assumption that a of x is in L infinity of omega, and by n this is a matrix. And what that means is that it's bounded. There is a more rigorous definition of what L infinity is, but we're just gonna it's bounded. Okay. So we were saying before that, okay, we only need one derivative of u, and it doesn't even need to be like a classical derivative, it just needs to be a weak derivative. Moreover, this would make sense. This equation still would make sense if grad u is only square integrable. So it doesn't even need to be continuous. So it doesn't need to be a classical derivative. So of course, this is provided that grad phi is in L2. And our test function, the test function that we're going to consider, grad phi is indeed in L2. Okay, so what do we let's summarize. So we only want you to have, it's possible for you to only have weak derivatives, and that you need only it only needs first order weak derivatives, and if this is in L2, this is bounded. For this integral to make sense by Hilbert's inequality, you only need grad u to be in L2. So the punchline finally is that this would make sense if u is in W12 of omega, or notation wise it's written as H1 of omega. The reason it's H1 because one can actually show that it's a Hilbert space. So what's a Hilbert space? It's an inner product space that is there's a definition, but what you need to remember is that it has an inner product. It has a way of looking at the dot product of vectors of stuff, something like that. You can think of functions that are as vectors. Okay, so it's a Hilbert space. So I'm digressing a bit. Okay, so what we have so far is that this makes sense if u is in W12. Okay, so let's see. We started off with this equation, negative divergence of a grad u plus cu is equal to f. And here, roughly speaking, you want u to have classical second order derivatives. Compare that with this equation plus cu equals fu, whereas here you only need u needs only L2 integrable first order weak derivatives. Sorry, wait. Or u is in W12. Okay, so let's see. So we started off with, if u is a classical solution, it needs a lot of things for this equation to make sense. But we know that if u is a classical solution, it also needs to satisfy this. And in fact, this equation still would make sense if we require less of u. In fact, if u is just in W12, which is very different from C2. So C2 functions are W12, but not vice versa. Of course in a bounded domain setting where we are. Okay. So we focus now on this one. So we know that a classical solution solves this, but just focusing on this one, and trying to see the functions u that satisfy this, and then probably show, well, okay, how many weak solutions do you have, and is a weak solution like a classical solution? But I'm getting ahead of myself. So focusing on this one, the solutions to this one is what we call a weak solution. Okay, so it's a weak solution because, so let's write that down. Solutions to this is called a weak solution. And it's a weak solution because you require less from u. So instead of it having classical second order derivatives, you only want u to have L2 integrable, like first order weak derivatives. Okay, okay. So let's make that formal. So we say that u is a weak solution of star if, okay, 1, u is in h10 of omega. So these are just functions that are in w12 and have trace 0, meaning to say, remember trace is a generalization of like boundary value, something like that. So you can sort of interpret it as you having 0 boundary values, which what we want from you. Remember, equation star is a Dirichlet problem where we want you to be 0 on the boundary. And, okay, and we want that for every test function, phi in h10, the following holds. You want a grad u dot grad phi plus cu phi is equal to fu over omega. Now, you might be wondering, like, okay, wait a minute. In the earlier derivations, you had that phi is in C infinity 0, and now it's not there, like h10 is something else. Now, h10 can also be characterized as, this is the closure of C infinity 0 functions in the H1 norm. Or in this norm, grad of something L2. And it's a technical thing that these norms are actually equivalent in H10. Okay, so, and then you can argue by density, that if you have that you satisfy this for every phi here by density, this must also be true here. So might as well just check it for every function in H10. Okay, so that is our weak solution. So it's weak because we require less from u. So we only want u to be in H10 instead of C2 and it to satisfy this equation. And a classical solution is going to be a weak solution. Okay. So let's draw something quick here. Okay, let's see how much I wanted to discuss. Okay, we're getting there. Okay. So let's just draw something here. Use this one. Boop. Let's use this one, bigger one. Boop. Okay. So in the case where omega is bounded, and we're always going to be working with in bounded domains for in this like discussion. So in that case, the set where classical solutions live, C2, so classical solution, is contained in the set where weak solutions live, W12 or H10. Now let's just put in W12. Weak solution. So, okay, so let's see what's happening here. Another reason why we want weak solutions is that it is easier to show that a weak solution exists. And the heuristic sort of is, so imagine this, does it make sense that it would be easier to show that something is in this larger thing than saying that surely it's in this smaller thing? So I like to think of it that way, that there is a price that I'm paying here. So some kind of a loss of accuracy, it's the price I'm paying. So by requiring less of my solutions, it makes it easier for me to find this new notion of a solution. So that's why we're looking for weak solutions. It's gonna be easier to show that a weak solution exists. And in fact, there are some equations for which no classical solutions exist, only weak solutions. And this leads us to the following questions. So number one, when is a weak solution a classical solution? And the answer to this is pretty much regularity theory. So this is regularity theory. Like, can we say that the weak solution has better regularity properties? Is it continuous? Are the derivatives also continuous? So it's a highly non-trivial thing for PDEs to show that weak solutions are in fact classical solutions. In ODEs, I don't think it's the same difficulty. Might be easy to show that weak solutions are classical, but in PDEs it's different. So the set of lectures that we're gonna do today, after this preliminary video, will be looking into that. We'll be like trying to prove that under certain conditions, weak solutions actually have better regularity. That they're gonna be Hilbert continuous, that their derivatives are also gonna be Hilbert continuous. Okay. The second question is, and this is one that we're sort of gonna dwell into today, is why? Okay, why is it easier to find a weak solution? Okay, so the short sort of naive answer is that we have access to better tools, quote unquote better tools, if we look in these larger sets, larger spaces of solutions, of possible solutions. Okay, so to illustrate this, let's look at a particular example. Okay. Let's look at an example. So let's recall something from linear algebra. So let's recall from linear algebra. If I have a linear functional A from some vector space V over R to R. So our field is R. It's always going to be R in these discussions. And V is finite dimensional, so dimension of V is finite. Then there exists some vector C and V such that A of V is equal to the inner product of C and V for every little v in big V. So this is fairly easy to prove. In fact, C would come from the matrix representation of A. So this is not difficult. Okay, so this is easy. So in finite dimensional settings, linear functionals have this sort of representation. You can find a vector C such that its action is just going to be an inner product. Okay. Now in the infinite dimensional case, we have something similar. So in the Hilbert space case, okay, so H is a Hilbert space. So it can be infinite dimensional. Let's consider a map from H to R, and it's linear. Then it is true that there exists some C and H such that the action of A on phi is gonna be the inner product of C and phi for every phi in H. And this is the Lease representation theorem. So I'd like to think of like spaces with inner products as something having geometry, because you can talk about orthogonality. So what I'm saying here is that even in the infinite dimensional case, you have access to these like geometric things, like an inner product or orthogonality. And in fact, it's helpful to prove this result, to find this vector C, for which the action of this linear functional is very simple. It's just gonna be an inner product between two things. Okay. Now, the example that I'm gonna tell you is, so the reason that we're doing this is we are asking why is it easier to find weak solutions. Okay, so we're gonna look at a particular problem, a weak form of a problem, and show that a solution directly is implied to exist by the Lease representation theorem. Okay, so it can be shown that H10 is a Hilbert space. Okay, and the inner product in H10 is, so UV is gonna be grad U dot grad V. So this is the inner product there. Or another equivalent one is just like UV plus grad U not equal. Let's make something like this equivalent. Grad U dot grad V. Okay. So it's going to be a Hilbert space with respect to any of these inner products. Okay. Now, because it's a Hilbert space, we have access to quote-unquote geometric tools, i.e. we have inner products and we have the Lease representation theorem. And we're going to exploit those tools to show that a weak solution to some PDE exists. So note that not every solution space is going to be a Hilbert space. So for example, C2 is not a Hilbert space. I don't think so. Hilbert space. And to show that something is not a Hilbert space, the common thing to do is to show that the parallelogram law doesn't hold. Does not hold. Okay. But note that this is a norm space. So there's a norm here. There's a way to measure distances between two things. Okay. But yeah, my point here being is that this Sobolev space is a Hilbert space, whereas the space of like classical solutions, where the classical solution would live in, it's not a Hilbert space. And it's good to work with Hilbert spaces because you have access to like quote-unquote geometric tools. Okay. So, okay, we're almost done. So, let's look at a special case. So, let's look at the case where A is in L infinity, so it's bounded. It means to say like it doesn't go to infinity or something like that. It's a function of x. Okay, it's symmetric. Okay, and that we have this one. And we're gonna explain what this means in a bit. So these are matrix inequalities. So what this means is that, for example, this means that A minus lambda I is positive semi-definite, or put another way, you have AV dot V is greater than or equal to lambda V squared. Uh, Note that A here is a function of X. So this is true almost everywhere X and for every vector V. Here lambda, big lambda are positive. So you can say something similar to this inequality here. This just means that A of X V dot V is less than or equal to big lambda V squared almost everywhere X for every vector V. Okay. Now, let's look at the problem. Negative divergence of A grad U equals F in omega. Omega is a bounded open set with a nice boundary. And that U is equal to 0 on the boundary. So similar to our calculations before, the weak solution is going to be something of the form A grad U dot grad phi, we don't have the C term, is equal to F phi for every phi in H10 of omega. Okay, so let's copy that and bring it to the next page. Okay. Okay. So we're looking for a U that satisfies this. Now, it is fairly straightforward to show that this is linear. Moreover, this is bounded. So linear functionals are, at least in the spaces that we're going to be working with, are continuous if and only if they're bounded. So we're not going to go into details, but this is also bounded. So this is going to be a linear functional in H10. Okay. Now, the more interesting part is the other one. And for the other one is that because of the symmetry property, because of the symmetry property A transpose equals A, the boundedness, A in L infinity, and the ellipticity, so we call it the ellipticity condition, lambda I less than equal to this. Actually, I'm sorry, but this condition actually tells you that A is in L infinity already. Okay. So with these, if I write UV, this sort of inner product UV, so this is gonna be an equivalent inner product on H10. Okay. So this is a linear functional Fv. Okay. So what do we have here? I have a linear functional. If f is known, this defines this linear functional Fv. I want to find u such that Fv is equal to this, which is equal to this, which is an equivalent inner product in H10. Okay, so let's see. I have a linear functional and I'm looking for something in U such that let's write it here, such that f of phi is equal to u phi. And does that ring a bell? That is precisely the situation where the Lease representation theorem would be very helpful. So the Lease representation theorem tells us that if I have a bounded linear functional, I can find a vector u in the Hilbert space such that the action of the functional is just the inner product of u with that thing. Now the crucial thing here is you can't just like, okay, I'm just gonna define, say that this is gonna be an inner product. We didn't show it here, but these conditions, we sort of need them to show that this is an equivalent inner product. Okay. Now we can be sort of lax when it comes to symmetry. There is what we call the Lax-Milgram theorem, and it doesn't have to be this way. Like, it can have lower order terms, but you sort of need to work harder for it. But in this particular example, just a direct application of the Lease representation theorem already gives you a weak solution. So this is what I mean when I say that weak solutions, although they have less as compared to classical solutions, it's easier to show that they exist because you have access to, like, let's say in this example, to geometric tools that otherwise you don't have. If you look for them in the space of like classical solutions, or where classical solutions are supposed to be in. Okay, so yeah, so it's sort of like that. Like, I'm paying a price. I am paying by losing one order of differentiability from you. And the thing that I get from that is that it makes it easier for me to prove that a weak solution exists. So now the hard work is to show that in fact a weak solution is a classical solution. So, and it would heavily rely on like estimates and stuff like that. And in the next like 2 or 3 videos maybe, we're going to look at exactly that. Like, there are going to be like 2 things: perturbation methods, where we sort of compare it to constant coefficient equations, stuff like that, and De Giorgi and Moser iteration methods, where it doesn't really use perturbation. Now, I think the video is getting a bit too long, so I think I'm gonna stop here. And maybe for the next video, maybe we can like sort of recap like different notions of continuity, because for the next video, what we're gonna do is to show that solutions are Hilbert continuous. So the question is, so what is Hilbert continuity? So it's in fact something better than just being continuous or even uniformly continuous, but not quite as strong as, say, like Lipschitz continuity, which gives you like differentiability almost everywhere. Okay, so yeah, there's that. So it's gone too long, so maybe I talked a bit too much, but yes, so thank you. Okay, thank you for staying.